Okay, so my talk is called Production Systems Design and Implementation, and I'm Pete Court. So who am I? My main working life has been as an MEP project leader, mainly for the past 16, 17 years with Crown House Technologies, who are a Tier 1 MEP contractor in the UK and overseas. Started life as event draftsman. Now a lean construction consultant for the past 3 or 4 years. Discovered the concept of lean in 2000 when on a hospital project, as project leader, we were trying to implement what we call best practice. And Dan Jones turned up, who was then helping, who were then called Bovis Construction on improvement. That led me then to discover the lean construction world, and particularly the IGLC, the first conference I went to in 2003. And then was convinced to undertake an engineering doctorate applying lean to construction, but as a practitioner. And then I stepped out of contracting and started consulting in 2017. And the goal really is to help, as it says there, to transform what I've experienced generally as traditional construction into a modern process of assembly. So what I'm going to talk about is nowhere near the scale of what Michael has just showed, but I think it's equally as important. And also I'll start with the safety moment. And really this is to emphasize that everybody on a construction site, whether it's a commercial or industrial construction site, has the right to go home after a safe and productive day's work. And I guess by that, I mean, if you look around offices these days, they're generally ergonomically designed, and we have ergonomic workplace assessments. Can we say we do that fully across all aspects of construction through each of the phases? You know, from groundworks right through to completion? Probably not, but I'll just leave you with that thought. And I will touch upon that as the presentation steps through. So just something about the contents. So I'll talk about the aims and objectives of design for manufacturing and assembly. I'll explain what that means in a second. The expected outcomes and the methodology. Some health and safety stats. Something about ergonomics and productivity. DfMA and an MEP product family. A design resolution process, which emphasizes where to start the DfMA process. A little bit about benefits assessment, and then 2 case studies that I've been personally involved with. One is a healthcare construction project, a large one in the UK, and secondly, an industrial construction project in rural Australia in oil and gas sector. And then questions. So some clarification terms used. So, and I guess AWP and lean groups are trying to sort of establish what is all the terms used and the clarifications for them, but you might hear me say these things. So pre-assembly, when I say this, I refer to prefabricated parts and small components assembled together off-site into modules. This is generally made to order. So if you just quickly look at the picture, you've got prefabricated pipe spools, nuts, bolts, gaskets, washers, etc. Equipment, and they are assembled into modules. Prefabrication refers to components themselves joined together off-site, although that does take place on site, welding pipes together, etc. Pipe spools, for example, generally made to order, and then loose components, which are nuts, bolts, straight pipes, interconnecting things, etc. What I didn't put on there actually is when I say DfMA, design for manufacturing assembly, that refers to the whole process. Design right through to completion of assembly. So what are the aims and objectives? So you've heard me say that, to transform traditional construction into a modern process of assembly by applying a DfMA process, field work to be only assembly of modules and kits of parts to form complete structures or systems, or integrated structures and systems, as the case may be, designing work with ergonomic principles, synchronizing all steps in the project value chain and balancing that work as well, adding value at each step in the project value chain, and in a lean world, The customer is the next step in the process. So you want to try and add value for the next step in the process, for example. And targeting, you can target, whatever you think is viable, but targeting much fewer site operatives, carrying out safer, more productive and simpler assembly tasks for a shorter period, and obviously with the appropriate equipment. So expected outcomes: to satisfy customers' needs and requirements, and not forgetting customers exist at all levels. To look after our people, and to repeat myself, everyone has a right to go home safely after a productive day's work. To challenge and change the poor image of construction because of increasing time, cost and resource constraints, and really to bring a high degree of certainty to what we do, which again points to safety, quality, cost and time. And on complex buildings or complex industrial construction projects, to protect valuable commissioning periods, because if construction periods overrun, then commissioning periods get squeezed and we hand over a poorly, or could hand over a poorly commissioned facility. So the methodology is to develop and implement a production system and MEP products or structural products that projects use. Strong leadership support at business unit and project level, making rules and sticking to them, and driving processes through all of their work streams. And you'll always come up against barriers to change in our industry, but it's about understanding what those are and then developing countermeasures to overcome them. So a little bit on ergonomics. Is it about fitting the worker to the work, which I would say in my experience is what we do generally, or should we fit the work to the worker? So when I conducted my research, which was around about 2004-05, these were the statistics from the HSE, Health and Safety Executive in the UK. I won't read them all, but it's obviously a large industry in the UK. And in that period of time, many people have died as the result of construction work, but many more have been made ill. We have the highest rate of musculoskeletal disorders, mostly from back injuries from manual handling. And 38% of over 3-day injuries was associated with manual handling injuries, and 15% of all major injuries. And the biggest statistic, I guess, is that many construction workers are absent every day because of injuries caused by accidents. And many workers are off sick at any one time with work-related illnesses. So dangerous body movements we see, operatives bending, twisting, stooping, pushing, reaching, pulling, stretching, walking, using workers to lift is both non-productive and dangerous. And I would generally say I've seen that on many construction sites I've worked upon, not all, but many. From a productivity dimension, and this is as a MEP contractor, and this relates to the project I'm going to talk about a bit later, which was a £100 million MEP job on the hospital. This is a pie chart, obviously, and it divides the value of the project into these components. So subcontractors are generally 34% of the value. Direct labour, which is electricians, pipe fitters, etc., 17%. Preliminaries, which in the UK is the cost of delivering the project, which is engineering time, staff time, etc. Plant, which is hire of equipment, and materials, buying parts, 16%. So if you look at labour, 17%, and you apply that to the labour value of subcontractors, the value of a large MEP project, the labour value can be upwards of 23 to 25%. So on a £100 million project, that's £25 million worth of labour. So when you look at your margin that you're intending to make on a large and complex project of 10%, you only have to lose 10% productivity on your labour side, and you can see how quickly you erode your margin. And so you can work on large complex projects as a contractor and lose money because your labour gets out of control on large projects. So part of the process is to ship as much of that work off-site, and we've heard about that from Michael's presentation. And I've called this, well, it generic term for that is design for manufacture and assembly in the UK. And just to really briefly touch on the steps to undertake is to review the MEP design at the design stage, identify core systems and areas, deconstruct that traditional design and reconstruct it with an MEP product family. So what is an MEP product family? And that is if you divide MEP systems through buildings from the largest end to the smallest end, you start with energy centers and plant rooms, and that's whole composite plant rooms that may sit external to a building or on roofs, equipment or plant modules that sit inside structures, vertical distribution modules, which are risers, horizontal distribution modules go from risers to points of use, terminal distribution modules, which can be fan coils, crack units, VAV units, etc., all generally above ceilings. Electrical modular systems, modular wiring systems, buzz ducts and the like, volumetric spaces, which can be bathroom pods, and then everything else, which is a kit of parts. So how does having a generic product family or module family help? So if you take a design process from concept design through to developed design to technical design, and you can apply whichever stage you're familiar with, whether it's level of development or the REBA design stages, but you know they do divide into these stages, and then you're into manufacture and in-field assembly. If you start a design process without a product family, you can, whilst you're in the concept design stage, you're iterating through various stages with the design team, with the client, etc. And that increases in definition through to integration of all services and coordination, and then you're into detailing for manufacture. If you have a product family, then the possibilities of iteration can become less because you decided that you are going to modularize your plant rooms, your risers, your horizontal distribution, your terminal distribution, and it's just a matter of collecting the systems in such a way that you can maximize that. And what I've called here is to enable that even more is to set up for success, to make sure all of these foundations are in place before that process starts. And that is understanding customer requirements and understanding the core values of the stakeholders, deciding what the overarching aims and objectives of the project are, establishing DfMA guiding principles, which are the way people should behave together, DfMA design parameters, which are the product design parameters, developing ground rules, creating a common understanding for all the stakeholders, understanding engineering principles of the product family, how they fit together, how they interconnect, what tolerances you have to consider when you're fitting manufactured products into constructed products, for example. Michael touched on that slightly. Creating design guidance. So if the design teams are not necessarily familiar with this, then you have to develop design guidance. So that's embedded in the start of the process. Understanding all of the components and all the parts and their lead times, and which are made to order, which are made to stock, etc. And then understanding what benefits you get from this. So is it actually worth going through the process? And really this is to establish that you go through this process based on setting up for success with your products in mind, and closing down the design process as you go through, because obviously it's too late later in the stages to start reiterating and integrating different things. So just a table of what that means. So these are the REBA design stages, stage 1, 2, 3, 4A, which in the UK you might get the MEP engineer to do the modelling, and then that's handed to the contractor from 4A. So he develops it from 4B onwards. But understanding what that project-specific collaboration strategy is at the start, and then what is the DfMA strategy to make sure that's embedded in the engineer's model. So by the time it comes to the contractor, then he's just receiving that and developing it further. So generic product family, and again this can vary in the types of industry that you're particularly working within, but again, it talks about volumetric modules, equipment modules, vertical distribution, horizontal distribution, terminal distribution, electrical modular systems, building technology systems, kits of parts, which is everything else, and then when they're assembled together in the field, form complete MEP systems. The same could apply for a concrete product family, precast. You could draw the same analogy, and structural steel. So just some more pictures. These are courtesy of Crown House, who I work for. So these are whole composite plant rooms with building fabric, and they're separated to be able to, or sectionalized, sorry, to be able to get onto transport in and around the UK, and then joined together on site. Plant equipment modules that go inside structures and fully integrated with control systems and electrical drives, etc. One thing I want to point to as well is the amount of steel in a module, and I'll come back to this point, including floors, floor on a floor, and does the cost of this steel actually add value when modules are installed? Plant equipment modules, these were data center examples. Vertical distribution modules, just some more notes, multi-floor, multi-service, integrated platforms, match-fitted and location pins for accurate site connectivity. So you'll see here that they're assembled together on a production line in the facility, and these large match pin location pins bring one module into the next, so the pipes align wherever they were connected or joined in the factory. Excuse me. And then that's another picture of the same thing, vertical and horizontal distribution modules being assembled in sequence together. And horizontal distribution modules, electrical underfloor, and these are again data centers, and these were all pre-wired with the various looms for A and B feeds. And then right down to the small distribution systems that go off main modules into, let's say, hospital rooms. And these are put onto trolleys with minimalist frames on a last in, first out methodology. So you go along a corridor, for instance, this would be the first one, move the trolley along, this would be the second one, third one, fourth one, fifth one, and so on. Excuse me. And then terminal distribution modules. So these are fan coils and VAV units. Excuse me. Volumetric spaces, all familiar with that. Bathroom pods, for example. And then interconnecting kits of parts. 20 minutes. So in terms of benefits assessment, and I'm not going to read all of these, but this is a methodology developed at Loughborough University with industry called Impressed. And the reason I'm showing this is just to give you a quick glance at the benefits from a DfMA method over a traditional method. And it's more extensive than this, and we can get more information available on this. But and it's an exercise you should undertake with the stakeholders in the project, because you can say whatever you like, but you've got to get general agreement that all these factors have been considered and there's an agreement on them. So, for example, persons on site, number of personnel on site involved with construction or installation of the components. Against the baseline method, DfMA method is significantly lower, for instance. And so if it's green, it's a benefit. In terms of quality, same thing. And again, I'm not going to read through all of those. So if you get these packs, slides, then you can read them. But one thing I'm quite interested in, as well as quality and safety, is the cost of DfMA, because there are experiences where DfMA can add a cost to a project, and is that perceived to be of value to a customer? Because if you're saying to an end user that we can deliver your project on time, on cost, and safely, to the right quality, etc., then you would say that, wouldn't you? But how do you actually achieve that? So with DfMA, if you're adding the cost of all those frames that I talked about earlier, then should the customer pay for that? not necessarily so. So part of this assessment is cost benefit, and if you look at this line here, extra over structural materials, etc. And I don't think this applies in industrial construction and the modules that Michael was showing, because the steelwork frames themselves are part of the structure because they support everything that's within them. The extra over in that case would be any temporary steels to stop things moving during transportation. So against the baseline method, there's a higher cost for extra overstructural materials and special packaging. So when I skip to the case study project I'm going to talk about, we had quite a lot of corridor modules, and by a corridor module, I mean a hospital street above the ceiling. That's the main route for all the pipe services and electrical systems and medical gases, etc. And if you put those in frames, and the total frame cost across a lot of modules, and this project was 1,200 of them, can be quite a high cost. And those frames, other than the supports every 1,200 millimeters, don't necessarily add value. So we developed an assembly, transport and installation frame, and this is quite an old model of that, that shows you what we did. And ultimately, it takes all of that non-added value out of the module. So it's a quick video just to run through. Is that showing okay?
Yeah, it's showing good.
Okay, so we had four types of internal frame, Christmas tree call them, for a wide corridor and a deep void, narrow corridor and a deep void, and a narrow and deep void, and a narrow and shallow. So all of the frames were sub-assembled. We call this mass customization because the ATIF was the same, the frames are the same, the ATIFs were adjustable for those four types. But all the contents varied because the pipes peeled off at certain places in the hospital. And that was all driven by the model, and each of those was just assembled in that specific module. So 5 were assembled. We consumed 4 a day on site. 5 were assembled together. 1 stayed in the factory. 4 went off to site, and another 4 were made up against that. So they came to site. We had the head tracks fitted first, so no partitions. We had embedded halfens. So that took care of tolerances because they were railway lines in the hospital streets versus the opposite direction for the unit strut supports. Bolted those in and then took the frame away. So we had 40 of those ATIFs in the entire production system and only left the value-adding components when the frames are taken away. And those were reused again on another project. One factor you have to consider on that is the distance for the backhaul. And you have to factor that into your costing analysis. So adding further value into modules, this is another case. So this is in quite a large development in London. And there was a 180-meter long corridor of distribution piping, bus ducts, and containment for cabling. 3 meters above finished floor level. These modules were 6 meters by 3 meters by 3 meters, which is the transport envelope to get them to the site in London. We decided to build in accessibility, so we put a platform in there, and that gives not instant access, but virtually instant access to connect pipes together and pull cables, etc. Because without that, you would be sending guys up on small noops to then contort their way through various layers of things to connect, or even just layering as you come down from the top down. It separates work above and below, removes the constraints so people can walk underneath that. Overall, it was 70% less cycle time for this main distribution corridor and was 85% less on-site resource. So the expected benefit summary: lower on-site activity count, much fewer on-site operatives, simpler and safer assembly tasks for a shorter period of time, higher on-time completion probability, high quality completion, less waste and untidiness, commissioning periods not compressed, and your prime movers, your plant, is available earlier. So you can use that plant for either commissioning or heating the building, etc. So case study number 1. So this is the production system model that was the output of my research. And just to briefly describe this, parts were categorized into a manufacturing technique called ABC parts analysis based on Pareto. Few parts but high value is type A. Many parts but very low value type C, and type B's everything in between. And these are then subdivided into made to order and made to stock. And obviously with made to order items, you need safety lead time if you're running a just-in-time system. And made to stock items, you need a safety stock in your supply chain. The B and C come through a postponement function, which means, and that can be in the supply chain, just parts kitting these for delivery via a logistics function to the point of use. And modules go straight to the point of use on a call-off basis. And then the assembly, in-field assembly itself is the construction site. And this is divided into work construction zones. And in the case of this hospital, is about 1,000 square meters. And these are week numbers. So we have a takt plan, a balanced work plan, a week beat as well, we call it. So materials are delivered to zone 1 in week 1, which team 1 deployed. That could be modules, that could be ductwork, that could be drainage, etc. They move to the next zone a week later, and the next zone a week later, next zone a week later, and the next team followed in behind them, etc. All of these functions, we had specifically designed mobile work cells that we designed with electrical guys, duct fitters, etc., etc. So this is called Lean and Agile because we're really trying to take out the process waste on the site. And agility is no two kits of parts are the same. So this function gave specific parts for these guys these operatives, to use at the point of use when they wanted them. Right. So without describing in great detail, which unfortunately I could, the theory of the development of the production system, it's in this document here, which is my thesis. So it's easy to read. I'm not a great academic, but if you just put that into Google, you can download the document, and it's fairly easy to read, and it's got some fairly interesting research papers in there as well. But it talks about synchronization. Last planner, Glenn Ballard was my external examiner. Reverse pass scheduling, starting with the end in mind, which I know is a real AWP mantra. Digital engineering, ABC analysis, inventory analysis, DfMA, pre-assembly, takt planning, theory of constraints based on reading a book called The Goal, which is fantastic. Mobile work cells with ergonomic workplace design, and creating a common understanding for all stakeholders. So there's the hospital, and it's a brownfield site, as we call that in the UK. So all of these areas were a live hospital. So we basically had to create a space by moving a car park, by building a car park, and then building the first phase, maternity oncology, and then decanting various parts of the existing hospital into that, and then demolition to build the next phases. So it was 100 million MEP, multi-story car park, maternity oncology here, sterile services department here, hub and wards, diagnostic treatment centre, and a separate community hospital. Commenced in 2006 and completed in 2013. So this is just an example of takt planning. So what I guess you would call roughing. We call that MEP first fix, and we divided each of these stages of the assembly into processes. So building fabric process 1 was fit partition head tracks to form the corridors and rooms. We did some courtyard rainwater outlets in that period because they were physically separated in space. And then we undertook each of the roughing activities, each with a trade team in their own space for 1 week. And each team would then cycle to the next zone and the next zone and the next zone. So no one shared the same space unless it was specifically planned to do so. and they're physically separated in that space. And that just represents how one construction zone had a 50-week cycle time between all of the building fabric processes. So this was roughing, building fabric 2 was stud and first side, building fabric MEP2 was drops inside walls, etc., etc. And each of the processes had a sign-off buffer for quality hold points checks, and then move on to the next activity. So just to give you some indication, I think we achieved about 40% off-site, and that's because hospitals are quite, and especially deep plan hospitals, they're densely packed with services. So these are the streets, the hospital streets, the ATIPs that you saw. There's about 18 in a construction zone of 1,000 square meters. We displaced ducting through the rooms because that's a low maintenance item. All the high maintenance items was in the accessible areas in corridors. Because this is a PFI hospital, there's charges if rooms are taken out of use. So you want rooms to be not taken out of use very often for maintenance. So that also helps. But you can look at read the amount of parts in the model that would need to be managed if you were stick building that. And that's why, and the Crown House that weren't DfMA'd or didn't have a production system approach did see some quite serious cost blowouts, and that's covered in my research process. It's described. So every component was modelled, and that's not new these days. This is a few years old now, but there was nothing generic put in there. So every component was modelled. So we had a full bill of materials. Excuse me. So these are some pictures of the assembly process, the ATIFs. So you'll see the various sizes of frames here, Christmas trees, and the ATIFs themselves were adjustable. So took this center part out. The ATIF was narrower for a narrow corridor, and put another jig in there, and that was for a shallower ceiling height. So we standardized on 4 types. And then all the spools were assembled just from small bore copper. Nothing like the scale that Michael has shown, but nevertheless, something that absorbs labour. So 1,200 modules I described earlier, and only 48 ATIFs on site. So this was the module installation week. So the previous trade had gone through, putting cast iron drainage. These are what we called Thunderbird 2 scaffolds. I can't remember why we called them that, but they're scaffolds with steps up. So you just walk and do your linear work in a linear way, because if you're assembling linear work high level vertically by going up in one-man AWPs, then in a lean system moving up and down is a waste. So you've got your operatives moving linear, can't even say that word, horizontally to do linear work. It's late in the UK, by the way, sorry. So this is the ATIF deployed. These are the cast-in halfens. So there's nothing that doesn't add value when it's finished. And from a tolerance perspective, these could be quite out of tolerance, and we would still pick this up anywhere because of the slotted channels on the unistrut. And then everything off the modules was prefabricated. So these were standard components, services laid in the model. So these were fixed to the slab, and they either had containment on them, here and here, electrical containment, ELV and small power, and pipes below, or just containment or just pipes. So there's a multifunctional bracket. There's no cutting up of and joining things together. And then at Unistra point of use, we had Kanban part centers, and these were scaled for the Kanban. It wasn't, but we had two boxes of each of the Zebedee clips, nuts, bolts, washers, that sort of thing. And the logistics thing just topped these up when they were getting low. And really, it's all designed so that the operatives had everything at the point of use and didn't have to go. No stores. Okay. And the same with cast iron drainage. It was sort of a Kanban because.
Sorry, Peter, I just temporarily turned off your webcam to try to address a bandwidth issue. Seems to be lagging a little bit. Carry on.
Hello, is that...
Peter, can you hear us?
Everything okay?
I think so, yeah. We're just lagging a little. I think you're probably picking up now gradually. Can you hear us okay? Can you hear us okay, Peter? Sorry, everyone. Peter seems to have gone offline temporarily. I think he'll be back momentarily, but we will wait a moment.
Steve, do you?
Yeah.
I'm thinking that maybe what we should do is hand it back to. Oh, is he back?
Hello.
Hi, Peter. Can you hear us okay?
Yeah, can you hear me?
Yeah, your connection dropped out for a moment, so we turned off your webcam and then you went offline, but it looks like you're back and we can hear you okay. Did you want to try to carry on?
Yeah, I'll carry on. So I'm just going through the various. The slides are not actually working now. So ductwork was put into trolleys, delivered straight to the point of use. The duct fitters didn't have to stop work and go and offload lorries, etc. They just carried on assembling back for where to put the drawings and things, etc. And that's still valid today because whilst we might use iPads on site, we still have drawings. We even looked in the the plasterboard installation process, the amount of manual handling on that. So we bought a lot of stock Arvid equipment from Sweden. Summary of outcomes on the project. Commissioning period was not compressed. The first phase, which was maternity oncology, achieved a gain share. It was procured under a separate model, P21 as it called now. 44% by value were manufactured off-site by paid parts. We achieved 30% less on-site labour. For the corridor modules, 93%. Less workers exposed to lower risks for a shorter period of time, no reportable accidents. Good ergonomics, achieved by focusing on modular assembly and workplace design. Something you can't measure, funny enough, in construction, just on a project, on how much you didn't injure people, which is an interesting topic itself. And an improved quality of work for those on site carrying out simpler assembly tasks. And productivity gains by eliminating process waste. And all that's, the output of that is covered in greater detail in the document. So case study 2, Northern Water Treatment Plant in rural Queensland. So this is a work in progress project. And I guess the constraints on this is that it's inland. We had a very limited logistics envelope by road. We didn't have a pre-assembly facility in Queensland, so we did in New South Wales, which is 1,000 kilometres away, that made modular conveyors. We flipped them to make pipe modules and electrical modules, electrical distribution modules, sorry. So it was an EPC project for Queensland Gas, for their northern gas fields. Capacity of 80 megalitres to 100 megalitres a day. advanced water treatment technology. GE were the technology provider, combining disfiltration, SUF, submerged ultrafiltration, IX, reverse osmosis, and brine concentrators. So part of the project was constructing all of these large-scale ponds, and we developed the path of construction through the plant complexity, which was the main treatment plant, the reverse osmosis building, main process plant. So that's where we started first, and all the outlying pump stations here and here, very small pump stations were started later, but brought on time with the commissioning process from the raw water pond. So the particular issues we had: a remote location, extreme weather and difficult logistics, difficult working conditions and living in a camp, rusted work periods, fly in, fly out, and at the time there was many industrial projects going on across Australia. The sister project we were building was stick built. It was about a year in advance of this one, at major labour and cost, and time overruns. And these were critical to the schedule to produce gas to target dates. So what did we do? We targeted 70-60-30, as we called it, 70% off-site, 60% less labour, 30% less time. We self-delivered the integrated model, a comprehensive DfMA solution, 5 plant locations, 32 module groups, 262 modules in total, and we designated the kits of parts as a module, which in this image here, you can see all the interconnecting pipes between the modules. This is a module, this is a module. This is GE process kit, just sat on the round bases. Parts kitting strategy, mobile work cells scaled up, workflow implemented, last planner used, daily commitment planning, the construction through the plant complexity, and the goal is to achieve construction completion in the shortest possible time. So the site was in Wandoan. Our assembly facility we created was in New South Wales. We started later than planned because it was designed to be stick built. So the GE kit was sent to site, as were a lot of the pipes for. So this was backhauled to the assembly facility in the laydown yard. All of the components were brought into a laydown yard and were either assembled into modules where we made steel, had it galvanized, pre-assembled it, sent them on a line of balance basis of 3 modules a day, and then incorporated large GE kit that didn't go into modules on site. So again, self-delivery crews with appropriate equipment, I've called it. So we had a rigging crew to offload and place modules, very unionized, so only riggers could do this. Mechanical crew to interconnect mechanically, electrical crew to interconnect electrically, scaffold crew where required, integral access platforms, and you might see some images here to give access for connections, and that then added further value because that was available for inspecting joints from the FM point of view. Supplied the appropriate tools, mobile work cells and point of use kits of parts. Again, just some images of work in progress. So these were the BC towers that we made on site, off-site, on their side, and they were elevated on site. This was the one of the pumping stations. So precast units here and pre-assembled modules on top of them. And then kits of parts delivered to the point of use. I spent some time at the sister project, Kenya Water Treatment Plant, where we had a large laydown yard, and all the bits and pieces were then collected from there and taken to the point of use. And I saw gaskets and nuts and bolts in boxes in the mud, etc., etc. So we procured 20-foot containers, sprayed them white, gave them a reference, kitted them out inside, and then these were placed at the point of use. So we had gasket walls. So the logistics team set all this up and then collected all the various items from the isometrics where all the components were listed, put onto trolleys, industrial trolleys, and then taken off to the point of use. Workflow was driven by the module in-field installation. So bases were formed just in time, module assembly in sequence, process kit assembled in sequence, kits are parts assembled, next module group commences, all based over the rostered work period. And then we had a crews in the back roster that were doing prerequisite work to enable that to happen. Oops, sorry. So how did we do? So compared to the sister project, 84% of large bore was put into modules, above ground piping, 58% overall. The SUF tanks, 90% were formed off-site, precast panels, as were the clarified tanks. 70% less on-site labour associated with assembling the modules compared to a traditional method. 60% for the SUF tanks, 60% for the clarifiers. Overall, Kenya Water Treatment achieved construction completion in 100 weeks, or mechanical completion, sorry, and Northern Water Treatment in 63 weeks. So that was a 37% cycle time improvement and 20% less cost compared to Kenya Water Treatment. And I think that's it. If you can still hear me, that is. I hope that made sense.
So, Steve, could you put up Slido? And because of the little technical glitch we had, let's add an extra 5 minutes to the before we take our break. So that should give us time for a few questions. So if you have a question, if you could put it into Slido, and we'll pick it up right away. So, Peter, while we're waiting for a question to come through, it sounds as though the modularization is almost down to a science in terms of how to organize, how to set up, how to minimize waste. What would you say the biggest takeaway you have regarding modularization is? What would the golden nugget be for you based on modularization?
Well, I think you've got to have it at the core of your organisation, and not undertake DfMA for the sake of it. And it is in sort of general construction or commercial construction in the UK. It is becoming more common. I'm not sure it's designed, when designers take pen to paper or start the design process, I'm not sure they're fully engaged with that in terms of commercial construction. So I would say it's to allow the contractor to be involved in the design stage earlier, to bring that design through to a point where they can just adopt that, if you know what I mean. So it's exactly what Michael said. To engage early, it's much more effective. Would prevent more iterations in having to think about things, how to distribute systems through buildings, which you could do one way for a stick built and another way for DfMA. So it stops a lot of rework. So really engage early. That's counterintuitive if customers are going out for competitive tendering, because you may not choose a contractor until the stage 4A or that level of design is done. So that's a bit of a conundrum to overcome. But my recommendation is to start the process early. Another key takeaway you may have gathered from what I said is to design work itself, because assembling modules and using mechanical aids to lift them is way better from an ergonomic perspective than sending people up on scaffolds or EWPs to and lifting pipe work, cutting pipe work, well, joining it in situ, all of the stuff you would imagine stick building is. So engage DfMA early and design work itself with the workers that can design the optimum way of undertaking that work.
Okay, we have a question. The benefits are clear. What type of specialists are required to drive this?
So if we're talking about DfMA, in some sense, the UK may be different because we have MEP contractors, so you can, undertake combined modular design. I understand from my experience in Australia and to an extent in America that you only have mechanical contractors, electrical contractors. For example, I might not be right on that. But contractors that are experiencing the process, that are familiar with DfMA, and preferably designers that are familiar with DfMA. That's not to say that it can't be done, it will just be more effective.
Okay, thank you. We'll just take one more question. Do you have the kit parts point of use savings?
So that's an interesting one, because I think the kit of parts point of use saving is not overspending on the waste associated with workers looking for parts. Because part of the reason cost blowout for labour is that the operatives, and when you tender work, you assume a level of productivity and continuous work. If they don't get that, then you'll spend more money. So I think it's a methodology to not overspend money. I hope that makes sense, but DfMA itself is, whilst it can add costs, and I talked about that briefly, it's also an insurance policy, if that makes sense, to not overspending money and not losing money, blowing out costs on your labour budget. And that's from a contractor's perspective.
Okay, well, thank you. Thank you for that. We're going to head into the break now, and we'll be coming back at 3:40. Want to thank Peter for his very informative presentation. Just a couple of quick things. One, after the break, Amy Marks is going to be talking about the future of where we can take this. I think that's going to be a very interesting, eye-opening kind of presentation. So something to look forward at after the break. And the second thing is we have a number of subject matter experts in our sponsors. And if you haven't already, please take the time to go visit them. We've got AWP specialists, we've got lean specialists, we've got technology to support. So definitely, if you haven't, go to the sponsors. And the other thing is send messages either to the speakers or to the other attendees. Sometimes the best learning can happen from just connecting with other attendees. Thanks very much, and we will see you at 3:40 Central Time.